here. So I wanted to briefly review what we talked about, and we're going to build on that substantially today, looking at some applications. So last time we introduced from basic thermodynamics and the Gibbs free energy, we introduced the idea that a reaction cannot be at standard state. We have these activity coefficients and concentrations that go into the reaction quotient to represent that. We introduced the concept that delta G represents the maximum reversible work that can be done for driving a chemical reaction, or the work taken to drive that reaction, and it can be decomposed into sort of a heat and a entropy term, which we knew. We considered a thought experiment thinking about doing a chemical reaction versus an electrochemical reaction and partitioning that delta G into sort of the reversible. The delta G is the reversible work, and that's of course a partition from the total heat and the entropy component, and we could measure those in this thought experiment using colorimeters. We derived the Nernst equation from the definition of electrical work and the equality with the free energy. And we talked about how, you don't typically put the electrons as a reaction and as a reactant or a product in your Nernst relation, because these are incorporated into the fact that we use a reference electrode. So these E's are typically versus a reference electrode. And what we really mean is we really have an overall reaction. If you want the E's to correspond directly to a delta G, you need to think about the overall reaction, including your reference electrode that's occurring. We talked about equilibrium and the chemical potential, how the chemical potential is given by the differential of the free energy with respect to the number of species, how it has a standard state arbitrary term and an activity term. We talked about how under equilibrium conditions, or for a chemical reaction, I should say, the delta G of the reaction is the sum of the chemical potentials of the reactants minus the products minus the reactants. And we talked about electrochemical potential, which is this sort of chemical potential term, sort of the intrinsic chemical energy of the species, added to which it is added a classical shift of electrostatic energy, the ZQ phi or ZF phi in molar units. That's the electrostatic energy at a given electrostatic potential that must be referenced to somewhere. And we talked about how that referencing is important. Usually we reference to a charge, infinitely far away from the system of interest, but you could choose many different reference states for that. Okay, so we talked about the properties of electrochemical potential. I showed you this big table, and we'll talk about how to think about using electrochemical potential, chemical potential, electric potential, and these other aspects in some applications today. Okay. One of the things we also emphasize is thinking about what a voltmeter measures, and the key thing I wanted folks to understand is, of course, a voltmeter is an instrument that measures the flow of something and of current, and it uses that flow of current to understand what the driving force for the flow of current is. And the driving force is actually the difference in electrochemical potential of the electrons, not necessarily only the electrostatic potential. So voltmeters measure differences in electrochemical potential of electrons. That's what they measure. Okay. And we talked about how you actually need a change in total free energy to drive transport. So this is the transport equation. Shane will talk in much more detail about transport in electrochemical systems, also when driven by light. Let's see here. This is the drift diffusion equation that just comes from that, which we'll get back into in more details. And then we sort of ended here with a summary of the key points. Okay. And so today I want to spend some time and talk about some applications of this. And some of these are coming from this potential, the idea of potentials in electrochemistry, a sort of primer article that Shane and I together wrote with others. And then from there, we'll talk, if we have time, more about double layers, and we'll kind of dive into the details of double layers. Okay. So this is sort of the review of the key points I went through alone, fast in the last few minutes. So one key point that came out of the last lectures is measurements of potential differences, and I'll read these, are necessarily of the total free energy difference. So if you want to decompose those potential differences into activity differences or electric potential differences, or you need to have some sort of model, and you require some sort of assumption. So it's good to understand those. Transport of any species is governed by the spatial gradient in the electrochemical potential in electrochemical cells, spatial gradient in the free energy of species. At equilibrium, the electrochemical potential of any given species must be the same throughout the system. So if I think about that, I can use that parameter actually to understand the distribution of species and the electrostatic fields and potentials that develop at equilibrium. For any chemical reaction, this is a consequence of the previous. The sum of the electrochemical potentials of the reactants must equal those of the products when multiplied by their stoichiometric coefficients. Processes with very slow kinetics are typically ignored. Okay, so in practical sense, right, we talked a little bit about this, and we'll get to this more today, but if you have like a balloon with hydrogen and oxygen in it, we can ignore, if we want, the reaction of the hydrogen and oxygen and still calculate lots of things about the gas in the balloon if we assume that the reaction is slow. And the other thing I think is important, at least this is sort of an opinion, that typically when you're writing or speaking, you should tend to avoid the word potential alone unless it's really clear what type of potential you're talking about, because otherwise it can be actually quite confusing and difficult to follow your argument. Okay, so let's do some examples today. This will be kind of fun, actually. This will be fun. So here's a really simple one, and I'm going to ask for audience participation now. So consider a redox reaction, right? Here's the redox reaction. O plus some electrons goes to R. And I take a metal and I dunk a metal into an electrolyte. What will happen that contains this O and R? Okay. There's O and R in the electrolyte, say ferrocyanide, ferricyanide at some concentration, and I take a metal electrode and put it in. What happens? Who can give me an idea of what happens here, okay? Let's assume that you have so much O and R that even though you deplete enough, the transport's fast enough, you're not actually changing the activities very much, right? Okay, so what happens at this interface? How does this work? So originally, say I have an electrochemical potential of electrons in the metal that's this level. What's the electrochemical potential of the electrons in solution? Is there an electrochemical potential of electrons in solution? Are there any electrons in solution? What do you guys think?
4.4.
Okay, but so how would I think about the Fermi level of the solution? So the first answer to this, right, was the Fermi levels equilibrate, okay, which is right. Okay, but a Fermi level is implicitly linked to the electrochemical potential of the electrons. In fact, those are essentially the same thing, right? So what sets the Fermi level? Well, we can think about this. What was one of our rules, okay? What was one of our rules for this redox reaction? I'm going to say that at equilibrium, mu bar M has to equal mu bar S, right? Would you agree with that, Karun? Is a sum of the chemical potential of the electron, right? Plus, I guess, negative F minus, because negative charge, minus F phi, right? I could do that. Okay, but I want to define it in terms of this. So I can actually look at this chemical reaction, right? And if I say the electrons in the metal are in equilibrium with O and R, what can I say about the chemical potential, electrochemical potentials of each species? Can I relate what's on the left side, the reactants, to what's on the product? Can I relate these somehow? If I say they're in, right? So I could write that mu bar R equals mu bar O plus N mu bar E in the metal. Okay, you see that? So I can actually define the Fermi level of electrons, right, in the metal in terms of mu bar O and mu bar R. Okay, so this is actually really powerful to think through this stuff this way. So I can write that mu bar metal, right, is going to equal mu bar R minus mu bar O over N. And we can actually define this because these have to equilibrate, right? We can define this actually as mu bar of the electron in the solution. So we can actually define an electron Fermi level in the solution, even though there are practically no electrons. Of course, there is some probability of finding a free electron. It's not zero, right? So we can define that. Okay, we can define that. So how do these things equilibrate? I want to go back to the original question. So I can just start calling on people and the screening depth in a metal is very small, about a nanometer, less than a nanometer. Okay. So basically, because the charges are so mobile in a metal, right? Electric fields can't exist in a metal unless there's current flowing. So the charge all goes to the surface. That's one of Gauss's laws, right? The charge goes to the surface. So I think you're getting at the right point, Jennifer. There has to be an electric field, right? There has to be an electric field that affects the electrochemical potential of the electrons in solution relative to those in the metal, right? So imagine I call this phi 2 and phi 1. If there's a difference in phis across this interface, once these equilibrate, because charge is transferred, right? So you guys all learn about Schottky diodes and PN junctions. I think most people here know about this stuff. It's the exact same thing. This is a contact potential, right, between two phases. So let's do that. Let's get rid of all these notes. Let's see if I can clear this. And let's go to the next slide. So we define that here. The electrochemical potential of the electron in the solution, they need to equilibrate. And of course, how they do that is you get some positive charge buildup in the metal, right? Because in this case, you'll have some electrons transfer, right? It's downhill. The flux of electrons is proportional to the gradient in the electrochemical potential, right, of the electrons. So they're going to flow downhill originally if you just imagine you did this experiment. But they're going to leave behind positive charges. And Jen was right. There's some effect of the electronic structure of the solid on where those charges are. And for a metal, they're all at the interface. Okay, they're not sort of extended in a depletion region like you would find in a semiconductor. And then you have an excess in the double layer, and we'll talk about double layers moving forward a little bit in more detail, right at that interface, right? And that's what is equilibrating these, right? Because the chemical part of the free energy of the electrons in both phases is different to start with, and we're going to compensate it by some electrostatic energy difference. Okay, do the electrostatic energy difference. Take two metal. If I take two metals, say titanium and gold, okay, and I stick them together, titanium has very active electrons, a high Fermi level. Gold has stable electrons. They're going to transfer, okay? And at that interface, you're going to have a buildup of charge. But a metal is very conductive. So the charges will accumulate at the very interface, as close as they can get to the interface to lower the free energy of the system, right? To lower the energy of the system. Electrostatically, they'll be attracted to each other. And so this is, the skin depth. We call it the skin depth of the metal. It's less than a nanometer. It's very, very, very narrow, okay? Now, if I do the same experiment with a semiconductor, okay, so now instead of titanium, say I take N-type silicon. Here's the valence band, conduction band, the valence band. Here's the Fermi level. It's sort of in between the bands, right? And I do the same experiment. Then what happens is you get band bending. And why is that? Well, you get that because you don't actually have any free positive charges, or you have very few in N-type silicon because you only have majority carriers or electrons. So when you try to build up positive charge, you actually have to build up positive charge via the ionized dopant atoms, which are spatially separated. And so that's why you get a depletion width, okay? And on the other side, you can still have your ions. Now, these ions are also distributed over some width, and we'll talk about that. That's governed by the thermal energy and the electrostatic energy via something called Poisson-Boltzmann equation. And we'll go through with that. So that's kind of how to think about that. And that's kind of depicted here, where actually the solution, this is the Debye screening length in the solution. And we'll talk about how to calculate that. Okay, great question, James. Other questions? Okay, let's keep going. And this is interesting. We can define electrochemical potentials, Fermi levels for solutions, even though there are no electrons there in principle, or very few. Okay, let's go forward. Oh, another point I'll make here is we've showed this surface to be initially uncharged. Okay, but real surfaces, we'll also talk about this, have some charge on them due to specific absorption effects and equilibration with solvent and things like that. We'll talk about that as we move forward in these lectures. It's very important in electrocatalysis and in thinking about interfacial phenomena in electrochemical systems. Okay, so here's basically what we just did. We said we can define the solution potential as of electrons, and here I've divided by F just to get to work out in terms of a potential, as a difference in the electrochemical potential of R and O divided by NF. And so I can work these things out in terms of their activities and the electrostatic potentials of the different species. And essentially I get a Nernst equation. So I can basically say that the solution potential is defined by this Nernst equation. You'll notice there's actually this electrostatic potential term in that Nernst equation. And this is because I haven't actually referenced this to anything. So this comes out of the referencing. So if I define E sol versus a reference electrode, and that reference electrode is in the same electrolyte at the same electrostatic potential, this term will go away. Okay, but this gives you a very nice definition of when you say, what is the, we'll often write on a band bending diagram, right? If you look at some like, Nate Lewis papers or anything of these photoelectrochemistry, you'll see kind of EOR, ferrocene, ferrocinium, or OH minus O2. And what does that mean? Well, it's given by the Nernst equation, and it's actually directly related to the electrochemical potential of the electrons. Okay, because that's what's equilibrating. It's the electrons are equilibrating across the interface. Now, the electronic carriers in the electrolyte are redox species, right? But we still need to define that equilibration process in terms of the relevant species that are transferring. Okay, going. So this is sort of a summary. So the initial difference in mu bar E drives charge transfer, leading to the electric potential drop. The amount of charge transferred depends actually on what the capacitance of the electrode, right? So it's going to depend on how that electrode, how its a potential changes as charge accumulates. But the amount of charge transferred is small compared to the number of electrons in the metal and the number of redox species in the electrolyte. So we don't think about changing their activities much, okay, or at all. And we'll talk about Poisson-Boltzmann, how these ions are distributed in the double layer. This is the double layer. If you go double layer, right? That's a topic that we'll go into great detail, I think, next time. And another key thing is mu bar, electrochemical potential after equilibration, is the same for all species everywhere, the ones that can exchange. Okay. So let's do another example. This one's a fun one. I like this one because we talk a lot about in LiSA membranes, right? We use Nafion and AEM membranes and bipolar membranes. How do I think about membranes? So let's consider a membrane. So let's start with two solutions with different concentrations of, say, KCl. Okay. And let's start that they're at the same electrostatic potential. Okay. There's sort of two, let's do a thought experiment. We have two sort of volumes, okay, and they're the same electrostatic potential, but they have different concentrations. And so because they have different concentrations, they're going to have different chemical potentials, right? So I can kind of think about the electrochemical potential as sort of the free energy of the electrostatic energy plus the chemical potential, right? So this is the electrochemical potential. So if I connect these two and I have nothing in the middle and I just put these two solutions together, what would happen? One is, say 1 molar KCl and one is 0.1 molar KCl. The ions will diffuse from high concentration to low concentration, which you of course know, but it's just the way I framed the question, right? So, okay, so what would happen if I didn't put anything in between these and I contacted these two things? Everything would move until the electrochemical potentials of all the ions was the same everywhere. But now what happens if we put here a membrane? Okay, and then it's an ion selective membrane like Nafion. So Nafion primarily conducts cations. So we're going to assume right now it's an ideal ion selective membrane, only conducts cations. So the cations want to move this way, right? But what will happen, Parker, when those cations move? What will happen? What will those anions do? If I have excess anions on this side and excess cations on this side, how's that going to change? Collapse to the membrane to lower their energy, and this is going to be Poisson-Boltzmann again. There's going to be some thermal entropy trying to move them apart, but there's going to be electrostatics holding them together, and they're going to be in general next to the membrane. And what's it going to do to Phi? What do we know? If potassium can transfer across this membrane at equilibrium, what can we say? Electrochemical potential is equal. Somehow I have to move this up, right? Well, one way to do that would be to move Phi up, right? So let's do that, okay? So we can move Phi up, right? We can increase Phi by creating, a double layer across this membrane. So it's actually very similar to the metal electrode in solution. We've now created an ionic double layer here due to the selective transfer of potassium across that interface, such that these two species equilibrate. And now the chemical potentials are different. So I still have higher concentration on this side, high, low, but I've compensated for that through the electrostatic energy. So Phi, right, increases on the right side. Okay, so this is a Donnan potential, and you can actually solve this. So you can say, this really is a really simple example. I can say, well, the chemical potential of potassium on the left and the right in the alpha and beta phase, say alpha is over here, beta is over here, they need to be equal. I can write that out in terms of a standard state and activity term and electrostatic term, right? And then I can just solve for the potential difference across the membrane. And you get that it's Nernstian. So it goes as the log of the ratios of the activities. So this is actually where membrane potentials in part come from. This is an important thing, I think, to understand when you're working with all types of membranes. You can use this analysis to understand them. Now I have a trick question for you. What's the chloride do? Okay, so what's interesting about this is we've actually assumed something here. We've assumed that the kinetics for chloride, so if I wanted to write a chemical reaction, this is why I say you have to understand what things you are assuming about your system. But if I have chloride, in the alpha phase going to chloride in the beta phase, I'm assuming that the rate constant is 0. I'm assuming that reaction doesn't happen. So what that means is mu bar chloride alpha is not equal to mu bar chloride beta. Chlorides aren't in equilibrium, right? So in reality, when you have a piece of Nafion, it will actually have some limited mobility of chloride, right? And so there'll be some chlorine crossover with time as they try to reach equilibrium, but you'll still actually measure a potential that's pretty close to this ideal limit, okay? And Shane knows lots about this stuff if you have more questions. And Adam down here, Adam's listening too. Adam Weber knows this stuff better than anybody else that I know. Okay, so one way I like to think about this is if you think about actually measuring this, measuring a membrane potential. So you might remember or recall in biology, cell walls actually have cation selective pore channels. Okay, and there's actually a membrane potential across the cell wall. In fact, one of the ways antibiotics work is they disrupt this membrane potential. They facilitate the transport. They act as ionophores that facilitate the transport of ions that biology doesn't, and they collapse this cell wall potential. So if you wanted to measure this cell potential, or you had a piece of Nafion and you wanted to measure the electrostatic potential, I wanted to measure this across the Nafion. How do I do it? So how do we measure electrostatic potential changes in an electrochemical cell? So can we do it with a voltmeter? I mean, maybe, but what I just told you is the voltmeter doesn't measure electrostatic potential, right? It measures electrochemical potential. So how do we do this? Does anybody have any ideas how the details? It's kind of interesting. So what you're doing, so here's like an example. So often if you're like, you guys could do this if you're working on CO2 reduction or whatever chemical system you're working on in LiSA. You can take two identical silver chloride electrodes and imagine that there's some potential difference across here, right? Some delta phi. And we could put those two reference electrodes in two different compartments and we can measure a voltage between them. So what does this voltage? This voltage is delta mu bar of the electrons, right, in the silver, right? It's literally what I'm literally measuring is the difference in free energy of the electrons in the silver wire. So why would they be different on this side versus this side? Okay, so this is kind of interesting. So if you think about it, the electrochemical potential of the electrons in the silver, okay, because this is chemically, a reference electrode is a electrochemical reaction at equilibrium. It has fast kinetics. So I can write that, right? So let's write that out. It's AgCl plus an electron, right? In the silver wire goes to Ag plus Cl minus. So I can write that as products minus reactants, right? So that's just the definition of equilibrium based on electrochemical potentials of the different species. And what you see is it involves the electrochemical potential of chloride. So is the electrochemical potential of chloride going to be the same here and here if the concentrations are the same? So I know that when I put a voltmeter between two anythings, right, what I'm measuring is the change in electrochemical potential of the electrons. That's what I'm measuring with the voltmeter, okay, between the two leads. So if I want to understand what this delta phi, this change in electrostatic potential is, somehow I need to relate it to the voltage I'm measuring, because it's not measuring an electrostatic potential directly, right? That's not what the voltmeter measures. It measures a change in electrochemical potential of the electron. So then I say, well, okay, what is the electrochemical potential of the electron in a silver wire? Well, it's given via the chemical equilibria, the electrochemical equilibria. I can write an expression just like we did before, right? And I can solve for the electrochemical potential of the electron. So, and I said, well, okay, this term, silver, I mean, the electrochemical potential of silver, this is uncharged. So it's not going to depend on potential, is it? This is uncharged. It's not going to depend on potential. This is the only one that's charged, right? So this one, kind of giving you the answer here, will depend on potential, right? So, you know, even though the activity, the concentration, say of concentrated potassium chloride in both reference electrode, even though the activity is the same, the electrostatic potential they're sitting at is different because they're on they're on opposite sides of the membrane. And there's a delta phi across that membrane. And so what that means, if their electrochemical potentials aren't the same, then the electrochemical potentials of the electrons aren't the same too. And you can work out that this difference is exactly equal to delta phi over F, probably with a negative. Okay. So you actually measure delta phi over F, or delta phi, because it's in volts, right? Because the voltmeter doesn't measure free energy, it measures it in volts. But the free energy difference is entirely given by the electrostatic energy difference in this case, right? But what's interesting here is this implies that actually the system's not at equilibrium, which is kind of interesting, right? So you basically have these two reference electrodes sitting on opposite sides of a membrane, but they're not at equilibrium, right? And they're not at equilibrium because there's a concentration gradient in potassium across this membrane. So it kind of depends on, again, what you define as equilibrium and what sort of processes you consider. Okay, but the chlorides are in different electrostatic environments. Okay, so so here's one that's really relevant. Okay, I chose a fuel cell here. It'd be the same thing for a battery. So I think most people know how a fuel cell or an electrolyzer is just running a fuel cell in reverse. This case I've chosen again Nafion. So it's a proton selective membrane. It's an electrolyte, right? That conducts protons and can go both ways. And what you typically do is you put some platinum on one side, some platinum on the other side, and there's various electrode architectures to supply and collect current. But imagine we can wires to this platinum catalyst, okay, on either side. And then I provide, say, hydrogen and oxygen on either side, right? How do I think about this from the framework that we have developed, okay? It's really useful. So I can think about locally, right? I can write this reaction, okay? So this is at the at the anode for an electrolyzer. And I have a reversible reaction going on. Imagine I'm at open circuit. What does open circuit mean to you guys? Ideally, right, there'd be no electron communication, right? So the electrons over here can't interact with the electrons over there, right? And so one way to do that, as you're right, James, would be have no wire. Another way to do that practically, if you're making a measurement at open circuit, is to put such a big resistor there that the amount of current that would flow if there was some difference in the Fermi levels of either side is so small because the resistor is so big that it doesn't perturb the Fermi level that you're trying to measure. Okay. And so that's what you practically do, right? When you take a voltmeter, so if you buy a cheap voltmeter at Radio Shack, I guess Radio Shack's out of business now, but electronics store, buy a cheap voltmeter, it might have a mega ohm resistance in it. So what that means, the input impedance might be a mega ohm. What that means is if you want to measure a volt difference, it actually requires you drawing a microamp of current through the device. A good voltmeter, like on your biologic potentiostat, is something like a tera ohm. Okay, so you're going to draw like a picoamp of current to measure a volt potential difference. So these are important things to remember in your measuring equipment. And what this means, though, practically, open circuit, we're going to assume no current can pass. So what that means is the electrons on the left side, on the anode, are not in equilibrium with the electrons at the cathode. So let's think about this reaction. So can somebody tell me how I would write the electrochemical potential of the electrons in the cathode, or the anode, sorry, at the hydrogen consuming anode? How would I write that in terms of the other species? Balance this, right? And it's right here, in fact, right? So that's the electrochemical potential of the electrons in the platinum. And then I can also write the electrochemical potential of the electrons at the cathode, right? That's consuming oxygen, or if it was electrolyzer generating oxygen. Okay, and this of course requires that you have one atmosphere present. So let's do a thought experiment. How would I make these what would happen if I shorted this out with a wire? What if I connected a wire? Okay, what would happen in this cell? What would happen as it's currently configured? Right, because here I have hydrogen. We know that hydrogen is a strong reducing agent. Oxygen's a strong oxidizing agent. So the reducing agent is going to donate electrons to the oxidizing agent, right? Okay, but those electrons are going to flow through the external circuit. And, if I just connect these things, in fact, their electrochemical potentials are actually not going to be equal to start with, because there's going to be an IR drop through the wire. Okay, right? But that's what's going to actually flow the current. That's what's going to cause the current to flow through the wire. And then when is the current going to stop flowing? How will the current stop flowing? How will you know when the current, how do we figure this out? What would be the conditions under which no current would flow? Right, so you basically would have to deplete your oxygen and hydrogen. And so at equilibrium, you might have, I don't know what the partial pressure would be, but it would be a lot lower than 1 atmosphere. It might be, 1 times 10 to the -7 or something like that on either side. Okay. So you're gonna deplete this of the reactants until you reach equilibrium. So it's important to think about this stuff actually in the context of a lot of schemes for splitting water and semiconductor photoelectrochemistry. They often don't think about both forward and reverse reactions and how that represents the net driving thermodynamic driving force and what represents true equilibrium. So a lot of times you'll hear things in photochemistry where like people say, well, the hole has to be below this, E naught for, oxygen. You have to the valence band, so there's enough thermodynamic driving force, but that's complete bullshit. Okay, because it's not the energy of the individual hole that determines the thermodynamic driving force for the system. Okay, it's actually the Fermi level of the hole. So what actually, of course, has to happen, people who have done this know, is in order for the net reaction to be forward, the Fermi level of the holes, the quasi-Fermi level, needs to be below the solution potential, not the valence band. So a lot of the language people use is very confused around these topics because there isn't a rigorous understanding of sort of how to think about the thermodynamic equilibrium in these types of systems. Okay, question for you. Right here, I have these things labeled A to C and A to A. What are those? Okay, good. Those are the overpotential. So how do those develop? Why do those develop? What's going on? So if I'm drawing a load, imagine I'm drawing a load out of here. So often I'll draw wires and I'll put a resistor, and that has some resistance. That's representing the work I'm doing external to my electrochemical system. That's the good stuff, right? That's the good stuff. So if I want to get this thing working at maximum efficiency, okay, what's the maximum work I can get out of this system? What is it, by the way? What would the overpotentials be if I was getting the maximum work out of this system, this chemical system? What would the overpotentials be? They'd have to be 0, right? Because the overpotentials indicate a loss of free energy driving force, so a loss of usable free energy. Okay. Okay, so I want them to be as close to 0 as possible because I want to get all this free energy. So the total free energy I could get out is 1.23 volts per electron. Okay, but of course I'm going to get less than that, and I get less than that because the electronic current is going here, but the ionic current has to complete the circuit, and there's overpotentials to driving that ionic current. So at this interface, right, I'm generating protons. At this interface, I'm consuming those protons. And each of those leads to the electrochemical reaction step. There's a reaction barrier. And again, there's a driving force in electrochemical potential that's causing the protons to move, causing the electrons to move, causing the reaction to go in the desired direction. But there's an activation barrier, there's heat generated, there's a loss there. And so Shane's going to talk a lot about this in coming lectures. There's also a loss moving through here. There's an ohmic resistance. So I'm going to have some gradient in the electrostatic potential moving in the Nafion. Okay. And that gradient in electrostatic potential is going to drive current based on Ohm's law, E equals IR, right? And that's going to give me a loss in the Nafion. So all those losses contribute to how much actual free energy I can get out of this system. I can flip this all around. If I'm doing electrolysis, the flip side is how much extra free energy do I have to put in to get out the 1.23 volts of my products, hydrogen and oxygen, at standard state. Trying to connect all these thermodynamic ideas to the kinetic ideas we'll introduce soon. Flows to the same in both directions. It has to do phenomenologically with something that people call the transfer coefficient. Shane will talk about that. And then practically, it also has to do whether your catalyst is actually chemically changing as a function of potential. So actually all the catalysts that do oxygen reduction and oxygen evolution, they're actually completely different surfaces under those two reaction conditions. So there's actually no reason that they need to be microscopic reverse mechanisms of each other, okay? Because they're different, actually different surfaces. Okay, so we talked about this. If zero net current is flowing, does that mean mu E of the electron at the platinum cathode and anode are the same? No, right? No, because at the anode, we can define the chemical potential of the electrons. I've actually given you a number here. I've defined it as 0 because these are, at standard state. These both have 0 at standard state electrochemical potentials if we take phi equals 0 on this side. Okay, so we can do that. Sure, why not? Okay, and then I can do the same calculation for the cathode, and I can calculate electrochemical potential of the electron in the cathode based on these terms. And then I can get an open circuit voltage of 1.23 volts, which of course we all knew, E cathode minus E anode, but now you can see how it connects fundamentally to these pictures of the free energy of the electrons, okay? And I mentioned this is an out of equilibrium. I like to think of this as out of equilibrium. The oxygen over here, the hydrogen over here cannot mix, right? So they set different, and the electrons cannot mix, so they set different electrochemical potentials of the electrons on the anode versus the cathode at open circuit. And that's why you're measuring a voltage, because it's not in equilibrium. But they're locally in equilibrium. At each electrode at open circuit, we can assume local equilibrium, just not global equilibrium. But again, it just depends how you define equilibrium. Some people would define these things a little differently and say the whole thing's in equilibrium. Okay. Good. Okay, so we mentioned this. So during operation, there must be gradients in mu bar for all species that transport electrons, ions, and water. So we talked about what drives the flow of H+. Well, here's the electrochemical potential of H+, right? Is this going to depend on current, mu bar? Okay, yeah. So it doesn't really depend on anything. It's not going to change with position usually, right? We're going to define that. Okay, and then the activity of protons is going to be pretty constant in Nafion because it's really high concentration of protons. Much like electrons in a copper wire, the activity doesn't change as you're passing current through a copper wire. So the thing that drives the flux of protons is the electrostatic potential, and that's Ohm's law. Okay, so that's basically Ohm's law will drive the current. Okay. So we talked about this a little bit. What drives the interfacial electrochemical reactions? It's this overpotential. We can define this in terms of the applied potential, electropotential, again, in terms of electrochemical potential of the electrons, if we want, versus the reversible potential for that reaction that we're considering. Here we're considering ORR, OER. Here we're considering HER, HOR. Or another way to define that overpotential is we can say, okay, at that interface, what's the equilibrium electrostatic potential across that interface? Remember, we say anytime you have a metal electrolyte interface, there's some equilibration leading to a delta phi, right? That was the first example we did. At equilibrium, it's something. And then the eta is basically how far I am away from that equilibrium, because that's sort of what develops the overpotential. Okay, so that's two different ways to think about the driving force for overpotential. And we'll get into more detail as we move into the detailed description of the double layer. Okay, so the last thing I wanted to do is just briefly talk about this, because I thought this is interesting and something that's very important in many contexts in LiSA. These things called electroosmotic effects. So does a proton exist as a free proton in water? Is that the best way to think about it? No. Usually we think about it as hydronium, and even hydronium, it has other waters that are sort of dipoles are oriented around it to stabilize that charge, right? That's why water dissolves ionic species so well, because it has a large dipole moment and it can stabilize those ions. Okay, so proton or an ion in general is going to have some waters around it, and it's going to pull those waters when it moves. Okay, it's actually going to pull water with it. So the flux of water, so I think about this fuel cell or an electrolyzer, there's actually going to be water moving in this system with the protons, actually pulling water from one side to the other. And we need to actually take into account that. And I'm not going to go through any of the derivations, but if you look at Newman's book, it's in there. Fuller and Harb has a very simple description of it, electrochemical engineering book. But basically, you could define the flux of water as essentially two parts. One sort of related to the driving force that's carrying ions. This is the conductivity for ions. This is the driving force pushing ions. And this is the electroosmotic drag coefficient. So it kind of says how much water does each ion carry. So flux of water will have that. And then we'll also have a diffusional term. So, if you are running a fuel cell, what can happen is you're going to pull water from this side to this side. This side can actually become flooded with water, and there'll be a back concentration flow from diffusion, and you have to balance all that in designing your fuel cell. Okay, and same thing in an electrolyzer. When you run an electrolyzer, you actually pull water onto the hydrogen producing side, a PEM electrolyzer. That water, you actually get about 8 waters, I think, per proton, and you'd actually separate that water out from the hydrogen and then feed it back to the anode when you're doing electrolysis. So this is all engineered, but it's important to remember this stuff, and it's critical if you start thinking about these systems. So the flux of water is actually coupled to the flux of protons. And the cool thing is, of course, it goes the other way around too. Protons can be driven by a gradient in chemical potential of water, right? So there's coupled transport. They're not independent of each other. So that's another important thing to remember. And this is particularly important in concentrated electrolytes and things like that.